Welcome to this lecture on research methodology. Today, we are diving into the fascinating world of research grants and fellowships. If you have ever wondered how scientists afford to build space telescopes, run massive clinical trials, or spend years studying marine biology, you are in the right place. Funding is the invisible engine of discovery. By the end of this session, you will understand exactly how researchers secure the money they need to turn their brilliant ideas into world-changing realities. Let us get started. Now that we know what our topic is, let us build some intuition. Imagine you have a brilliant idea to build a revolutionary new type of electric bicycle. The design is perfect, but you have absolutely no money to buy the motors, batteries, or tools. What do? You would likely look for an investor. In the academic and scientific world, this exact scenario happens every single day. Researchers have incredible ideas for curing diseases or exploring space, but they need money to buy lab equipment, travel to research sites, and even just pay their own rent while they work. This is exactly where research grants and fellowships come into the picture, acting as the financial fuel that keeps the engine of global discovery running. Building on that intuition, let us formally define what a research grant actually is. A research grant is a specific type of financial award given by a government agency, a private foundation, or an academic institution. Its primary purpose is to fund a clearly defined research project. Unlike a bank loan, this money does not need to be paid back, provided the researcher uses it exactly as outlined in their approved proposal and follows all ethical guidelines. A grant typically funds the project itself. This means the money goes toward tangible project expenses, paying for things like laboratory chemicals, high-performance computers, and compensation for human participants in a study. While grants fund the project, we must also consider the people doing the work, which brings us to fellowships. A fellowship is slightly different in its focus. It is a financial award focused primarily on supporting the researcher as an individual, rather than just buying equipment. Fellowships often cover a researcher's living stipend, their university tuition, and their professional development. Why is this important? Because it allows the scientist to focus entirely on their studies and experiments without needing to take on an outside job to survive. Together, grants and fellowships ensure that rigorous, high-quality research can be conducted by talented individuals, completely regardless of their personal financial background. Now that we understand the definitions, let us look at why this matters so much in the real world. The importance of research grants and fellowships simply cannot be overstated. They are the absolute lifeblood of modern scientific and academic advancement. Without this external funding, universities would only be able to afford basic teaching. Groundbreaking experiments would simply never happen due to their immense costs. In the real world, grants are used to fund massive endeavors, like the development of life-saving vaccines, the launching of space telescopes, and extensive sociological studies on poverty. Furthermore, securing these funds is highly competitive. When a researcher wins a major grant, it serves as a mark of prestige, signaling to the world that their peers believe their work is highly valuable. Understanding the importance of funding leads us to the practical side. How do researchers actually ask for this money? When a researcher applies for a grant, they cannot simply ask for a random pile of money. They must mathematically justify every single penny through a rigorous budget. The total budget requested is divided into direct costs, which are the actual expenses for the research, and indirect costs, which are overhead fees charged by the university. We represent this with the formula B equals D times the quantity 1 plus R. Here, B represents the total grant budget requested. D represents the total direct costs, like lab equipment and salaries. Finally, R represents the indirect cost rate, or overhead rate, set by the university to cover electricity and administration. If the direct costs, or the overhead rate, increases, the total budget B naturally increases as well. Before we move on, let us see this formula in action with a concrete example. A researcher is applying for a grant to study marine biology. They need $50,000 for underwater equipment and $30,000 to pay their research assistants. The university charges a mandatory 40% overhead rate. What is the total grant budget? First, we find the total direct costs, D, by adding the equipment and salary expenses together, giving us $80,000. This is the actual money needed to perform the scientific work. Next, we substitute our direct costs and our overhead rate of 0.40 into the total budget formula. The term inside the parentheses becomes 1.40. Multiplying the direct costs by this overhead factor gives us a final total budget of $112,000. This ensures both the project and the university are fully funded. Now that we have successfully calculated a basic budget, we must face a very common real-world challenge. What happens when the funding agency sets a strict limit on how much money they will give you? Many prestigious national fellowships offer a maximum total award, effectively capping your total budget, B. However, the researcher's host institution still mandates their strict overhead rate on all incoming funds. In this scenario, you cannot simply ask for more money to cover the university's fees. Instead, researchers must work backward to figure out how much money they actually have left to spend on their scientific equipment and personnel. This means they often have to scale down their experiments to fit within a strict funding ceiling. Let us look at how we calculate this spending limit. Let us apply our budget formula to this new scenario. A prestigious national fellowship offers a maximum total award of $150,000. The host institution mandates a strict 50% overhead rate. What is the maximum amount of direct costs the researcher can actually spend? We start with our known maximum budget, B, of $150,000, and our overhead rate, R, of 0.50. We plug these into our standard formula. This gives us 150,000 equals D times 1.50. To isolate D, we divide the total budget by the overhead factor of 1.50. This reveals that the maximum direct costs are exactly $100,000. Out of the $150,000 awarded, $50,000 goes directly to the university, leaving the researcher with $100,000 for their actual scientific work. Now that we have used this formula to solve a real-world problem, let us understand the general mathematical derivation behind it. In the previous example, we plugged numbers in first and then solved for D. But we can actually create a brand new formula to reverse engineer allowable project spending directly. We start with our standard grant budget formula, where the total budget, B, is equal to the direct costs, D, multiplied by 1 plus the overhead rate, R. This equation perfectly models the relationship between what the researcher needs and what the institution takes. To find the maximum allowable direct costs generally, we need to isolate D on one side of the equation. We do this by dividing both sides by the overhead factor, 1 plus R. Continuing from our previous step, let us finalize this derivation. By dividing both sides by 1 plus R, the overhead factor cancels out completely on the right side of the equation. This algebraic manipulation successfully isolates D, giving us our final result. D equals B divided by 1 plus R. We have just transformed a formula used for calculating total budgets into a powerful new formula used for calculating spending limits. This step clearly shows the mathematical relationship. As the institutional overhead rate in the denominator gets larger, the actual research budget D will become smaller. This is a critical tool for any scientist who needs to carefully design their experiment so that it does not cost a single penny more than their calculated limit. So, we have proven the math behind the budget, but where does budgeting fit into the bigger picture? This diagram illustrates the complete research grant lifecycle. It all begins on the far left with the idea and proposal stage, where the researcher writes down their vision and calculates the budgets we just learned about. Next, the proposal undergoes peer review, where other scientists evaluate its merit. If successful, it moves to award and allocation, where the funding agency officially grants the money and the university takes its overhead. Only then can we move to research execution, where the actual hands-on science happens. Finally, the cycle concludes with reporting and publication, sharing the new discoveries with the world. Every step is connected, and it all relies on that initial funding. We have covered a lot of ground today, so let us review the key takeaways. First, we learned that research grants and fellowships are the essential financial mechanisms that make advanced academic inquiry possible. Grants typically fund the specific expenses of a research project, while fellowships focus on supporting the individual researcher's living and educational costs. Second, we saw that understanding how to properly budget for these awards is a critical skill. You must always account for institutional overhead using our budget formulas, ensuring you know exactly how much money goes to the science versus the university. Ultimately, mastering this grant process is what allows researchers to turn their theoretical ideas into tangible, world-changing discoveries. You now have the foundational knowledge to understand how global research is funded.